This conference will now be recorded.
Okay, so good evening, everyone. Today we'll be discussing about the Leuenberger and sliding mode observers. Myself is Bharini Chandrakumar, and I'm a faculty at German Institute of Technology. More details you can see at my Google site. So today, the topics what we'll be discussing, the Leuenberger is from the first reference, and uh, and second and third reference will follow for will follow for the sliding mode observers. More specifically, we'll be following only the reference number 3, though the sliding mode observer what we are going to follow is more or less the same in 2 and 3. So the example we have will be the toy example will be taken from the third itself. So fundamentally, why the observers are required, or what is the purpose of an observer or a filter or the state estimator? More or less, all of them are the same. The terminology basically, in a very what I can say that in a very vague way or in a colloquial language, generally this observer is used for the plant which is not perturbed with sensor noise or observer noise. This in general the Leuenberger observer. Whereas if if there is some noise, if in the design if there is some noise component has been considered, like plant noise or the measurement noise, then we call it as a filter. This is very due to some historical reason, but more or less observers, state estimators, or filters, they are one and the same. Don't compare with this low pass filter or the high pass filter. I'm talking about Kalman filter and so on. So all three of them, it is just the naming thing. Sometimes people may say that sliding mode estimator, Leuenberger observer. Instead of Kalman filter, some people say that Kalman observer. So so it doesn't matter what the naming. So the purpose of any state estimator or the observer or the Kalman filter is to estimate the states. That is a fundamental thing. One can estimate the parameters as well, which is called as a parameter estimation. One can estimate the faults as well. We call that particular aspect as fault estimation. The key idea here is, in general, if you want to estimate simultaneously the states and parameter, what we do is we augment the states with parameter. So let us assume if my plant order is 10 and I want to estimate 5 parameters. So what I will do is, in general, if it is only the state estimation problem, if it is a full order state estimator, then I'm going to estimate only the 10 states. When I say that it is the combined state in parameter estimation, what I will do is with the existing state vector of 10, I will add the remaining 5 parameters as well in the state vector. So now my new augmented state vector will look like a 15 states. So if I am estimating the 15 states, so by default, since the 15 states, last 5 states are the parameters and the 10 states are the states, actual states of the plant. So in a way, I am estimating the complete augmented state vector, and hence the parameters also been estimated. For the faults also, the similar strategy can be applied. In general, as far as the control theory are concerned, there are 2 types of faults. One is basically an actuator fault. The second one is sensor fault. The actuator fault or the sensor fault, there are 2 things one has to do: the fault detection and isolation, and the next one is the fault tolerant control. Fault detection and isolation we'll be discussing in the tomorrow's class, and the fault tolerant is beyond the scope of this particular FDP. So why the state estimation? The purpose again is to reduce the total number of sensors. For example, what we had discussed in the very first day, if it is a brushless DC motor, basically there are 5 states, 3 currents, 1 speed, and 1 position, rotor position. So in general, if I want to avoid the mechanical sensor for some purpose, either the mechanical sensors are very expensive or very bulky or not accurate. So I want to estimate all the five states based upon only the three current sensors, IA, IB, IC, and the remaining two states I have to estimate. So I have to employ some kind of state estimator in that one. So which will basically take the three outputs. Output means from the three sensors I'll be using IA, IB, IC. From the three outputs, I will estimate the remaining two the remaining two states, omega and theta, speed and the rotor position. If it is a full order state estimator, I will be estimating the output state or the sensed state as well. So that will make us the five full order statements. All the five states are going to estimate. So in general, for the control purpose, if it is a full state feedback, I don't want all my states to to be measured using the sensors. So what I will do is some states I will use the good or the state for which the sensors are very reliable, very cheap, and very accurate. Those I will use for the outputs, and the remaining unreliable states, or the states which are very noisy or the sensors are very bulky, sensors are very expensive for those particular states, I will estimate by using my state estimator or the observer. So that is a fundamental requirement of an observer. So eventually it will reduces the total number of sensors required for a particular operation. One can argue that why to reduce the total number of sensors? Because if it is a very simple thing, yes, you may be having 5 to 10 sensors, but for a complex practical real life applications, there may be around 3,000 states. So you can't use the 3,000 sensors. If there is one sensor is faulty, then there is reliable sensor. If the sensor is unreliable, then it is not good to use all the sensors. So we have to choose judicially which sensors to be used for the state estimation. And simply, you cannot simply blindly you can choose whatever you want. The first and foremost thing for designing any observer or the state estimator, one has to ensure that your plant is observable or detectable in some cases. Observable or detectable. Very few observers, these conditions can be relaxed. In very few observers in it, with several assumptions, this can be relaxed. But in general, one has to ensure that always the plant should be completely observable, or it should be at least the detectable. Detectable means unobservable modes if they are stable. Suppose there are two unobservable modes, and if they are stable, that is called as a detectability. And if your system is detectable, then also up to a certain extent, with a limited with a certain kinds of trade-off, you can still use the state estimator, state estimation design. So in this particular lecture, we will be going to discuss two class of observers. One is the Leuenberger observer, and the second one is the sliding mode observer. The Leuenberger, the fundamental difference between both the Leuenberger and observer is that the Leuenberger observer does not assume any kind of uh, disturbance or any kind of noise in the design process. It may inherently reject some of these things, but in general, for the design purpose, it doesn't consider any such fault. I mean, disturbance or noise in the design. It is a very simple observer, and basically it is based upon the concept of pole placement. If you see the pole placement controller, what we ensure that closed loop plant or the closed loop system should always the closed loop systems, the poles of the closed loop system should be equal to the desired poles. And we had a detailed discussion on how to select the desired poles based upon the problem at hand. This Leuenberger observer is actually a dual of the pole placement controller. The principle of duality, what in general it says that if you can replace in general, in the duality means if two systems are dual, if let us assume one system is left and the other system is right, if this system A is equivalent to the A transpose, B of one system is equal to the C transpose, C of another one system is equal to B transpose of that system, then we call it as a dual then the system's left and system right are dual. Similarly, the controllability and observability are dual in nature. If you remember from the fundamental, textbook uh, control systems, the controllability for the finding the controllability, you need A and B matrix. The controllability matrix is B A into B, A square into B, up to A to the power of n minus 1 into B, where n is the total number of states. So that is a fundamental controllability matrix X formula. And if the rank of that matrix is controllability matrix is equal to the states of the plant, then we can say that the plant is completely controllable. So when we go for the observer design, so there is a separation principle. What it says that for a linear system, you can design uh, a controller separately, observer separately, and if both of them are optimal, if you combine them, then the resultant combined closed loop controller and observer structure will also be a stable or the optimal. So that is called as separation principle, and it has been exploited in several ways. The LQG, it has been very neatly explained, where we design the stable LQR and the stable Kalman filter, and which will ensure that my if I combine both of them, the good properties of both of them will still be retained. So that is the the separation principle. So when I say that this Leuenberger observer, so it is a dual of the pole placement controller. So duality means if you change B with C transpose, and in the K, whatever you are getting the pole placement gain, if I replace it with the corresponding the transpose of that pole placement gain, if I replace with the transpose will become the observer gain, Leuenberger observer gain. So so what I can say here is I will go. This might be a kind of revision for the only the Leuenberger and for the FDP 1.0 participants, but we have not detailed. We have not analyzed this Leuenberger observer in very detail, because the reason is that we have not gone for the sliding mode observer. So the purpose here is the Leuenberger observer is very simple, very straightforward. But why, if that is very simple and very straightforward, then why one has to go for another observer, or the so-called sliding mode observer? A similar example yesterday we have seen with the two different cases. In the very simple case, what we have seen that if you use a kind of output feedback and variable structure system, and we have seen that if we use one controller, the system may not look linear controller, the system may not look is not the initial conditions are not converging to the equilibrium point or the origin. Another case also, it is not happening. If I'm just considering the linear feedback law, u equal to minus ky. However, if I join both of them, if I combine with various structures, then we have seen that from any initial condition, it is possible to drive the initial conditions to the origin, the system's initial conditions to the origin. So that's what we have seen. And the second thing, what we have seen there is we have seen a very simple state feedback control, and we have seen the state feedback control works very fine. It was for a double integrated plant. It works very fine when there is no disturbance, or there is no external disturbance or so on. In that case, it is very good, very fine. The the normal state feedback control works very fine. It is basically a pole placement controller where we try to place the gains at various locations. But that property immediately, there is some problem with that particular design. If disturbance comes into the picture, that's what we have seen. It couldn't able to handle the external disturbance. We have put a switch and we have activated with we have activated with we have activated the switch for there are two options, one for the linear and the another for the sliding mode control. So as soon we have seen that linear controller is not capable to deal with as soon as if it sees the uncertainty or the fault, uh, some kind of fault in the system. But when we try to apply the sliding mode control to the same system, it works perfectly fine with both uh, disturbance and without disturbance. But the problem with the sliding mode control, what we have seen, is the issue of the chattering. And I have done some simulations which I will discuss if time permits today, otherwise tomorrow. With by doing a very small correction in the sliding mode control term, very small corrections, then most of the chattering goes away, and it solves it solves the issue of the chattering. Though it is a heuristic way, but very small change in the control setting. If I do, then this chattering goes away. Mostly it goes away with a little bit trade-off in the performance. That aspect we will discuss if time permits today, otherwise tomorrow. So in that way, this one does not need to go for the higher order sliding mode or integral sliding mode or any other or low pass filter. So there are three ways one can reduce the chattering. Either if you pass that high frequency chatted signal through a low pass filter, then obviously it will be filtered out. But since the filter has its own dynamics, so the input what you are giving to the filter and the output what you are getting, along with the frequency reduction, there will be small delay also. If it is the first order, then certainly there will be certain lag. You can expect certain lag in the input and the output. So that is a trade-off. The second way is to reduce the chattering by using the higher order sliding modes, and the third way is by using integral sliding mode and so on. Again, these are beyond the scope this lecture. Just I'm giving you the philosophical thing. uh, Basically, why, from where this sliding mode has started, this I forgot to tell you. This sliding modes have started in the Russia in a long back in 1960s or so on. But though it was published, though it was proposed in 1960s, in general it is called as a bang bang control and so on, this variable structure control and so on. But the Russian work, the Russian researchers there, uh, Utkin is the one who is responsible for bringing that sliding mode excuse me, sliding mode control to the English speaking community, or what are the papers we are seeing. So he's the one who has basically who is the main responsible for bringing the work from Russia to the English speaking community, or the English, so-called English journals and so on. So the Utkin, so basically it started in Russia. Yeah. So we will the first we will go with this Lienberger observer, and then I will show you what is the problem with the Lienberger observer, and then next I will go with the sliding mode observer. Okay. So again, it will be the hands-on. As soon as I complete this Lienberger observer, it will take 15 minutes. So by 17:15, I will try to end the Lienberger session, and then I'll be giving you half an hour or 45 minutes to run this one. So I slightly made this simulation a little bit tougher than as compared to the last one. So in the earlier one, I had given the skeleton and I had given you the PDF files. From the PDF file, you can easily copy the text and paste it there. But now I converted it to the images. So you cannot directly copy from the PDF file. So you had to manually type some 5 to 6 equations. So I want you to type the 6 equations. So slowly, I am making the things tough so that the learning will be good. So if you type that 6 equation, everything is in front of you. You have to just copy and paste, not copy and paste. You have to type manually some 5 to 6 equations only in the plant and the controller. So that will make sure that if you are getting the error, then you have to debug yourself. Otherwise, we are here always to help you out. So that way, slightly I made today the simulation will be slightly tougher than the one what we discussed yesterday. Not tougher in a way that as far as uh, the theory or anything is concerned, tougher in a way that you cannot copy directly the code from the PDF file to the simulink. Okay. So this is the Leuenberger observer. Consider the linear plant x dot equal to ax plus bu and y equal to cx plus du. In a very simpler case, what I assume that without loss of generality, I will assume that this d is 0. So x dot equal to a into x plus b into u, y equal to cx plus du. If this d is 0, y equal to cx. So, so this is the standard observer gain. This is the standard linear plant. And the observer dynamics. So the observer dynamics is something looks like x hat. Whenever I say this x hat, that means they are the estimated values or the observed. So what I want the x hat. That means the estimated values based upon the outputs. So only for the estimators, I have only this output information, the limited information, this y. I don't have the all the state information. That means this I don't have the complete information of x. That means if I assume that it is a brushed DC motor, and if x equal to 5, that means three currents, one speed, and one rotor position, the five states. But when I say that the output only three states are available, that means my C matrix will 1 0 0 0 and 0 1 0 0 0 0 1, something like that. So it will have only three components, the first which are relevant to the first three sensors. So Y is known to us. So what is known to us a priori is A, B. I know A, B, C. Since D is 0, we don't have to much worry about that one. So ABC is known to us, and we don't. We have this Y information, the complete Y that is from the output from the sensors. We don't have this complete X information. Only the part of the X information is required. So now what I'm going to do here is I'm going to estimate this complete state vector X hat. That means for the brushless DC motor case, I am going to estimate all the five states. So the idea here is what I'm doing is I'm assuming that E equal to X minus X hat, where X is the state and X hat is the observed states or observer states or the Leonberger states. So what will happen is if this E goes to 0, then what is going to here? X equal to X hat. So for the X hat design, I am only solely dependent only on the output. So this means that if X equal to X hat, I have the complete state information, or I have reconstructed the state, or I have re-estimated the state based upon the output information if this E goes to 0. So how do you make this E goes to 0 is the main concern here. So E can go to 0. So what we are going to take here is we are going to take the error dynamics. So our aim is rather than instead of E going to 0, we will ensure that E dot should also go to 0 asymptotically or so on. So if I take the derivative on the both side, then it is going to become E dot equal to X dot minus X hat dot, or d by dt of x, or dx by dt. Dx by dt I can get it from here, and the another one is dx hat by dt. So this is I can get it from here. So if you see this observer dynamics, so what are the things known to us? This A, I know what is A. This B, I know what is this B. This H, I know what is this. No, this H I had to find out. This H is unknown. So this is called as observer gain or Leuenberger observer gain. Y output is known to us, and y hat is not known to us. Y hat can be calculated as C into X hat. So C is known to us. So what we have to do here is, what is my aim here is E dot equal to d by dt of x minus x hat. If I substitute the x dot or d by dt from here, this expression, and x hat dot from here, then it is going to boil down to something like this. And if I substitute E equal to x minus x hat, it is going to become a minus hc into E. So what I want to do here is I want to make this particular a minus hc of, for what corresponding values this a minus hc, I have to choose this h should be selected in such a way that this e dot should go to 0 asymptotically. As t tends to go to as t tends to infinity, then my e dot should go to 0. So how it is possible? It is only possible if I select, if it is a scalar case, if this a minus hc is one negative value, then what is going to happen? Then if I integrate to get the e, and what is going to happen, the time domain, if you see the time domain solution as well, it will be exponentially decaying, provided this a minus hc is negative. If it is a scalar case, if it is a scalar case, only one value. If it is a vector case, then it will be a matrix. And we had to, how do you select this a minus hc? So what should be selected? If all the eigenvalues of this h a minus hc are negative, then it will ensure that e dot will go to 0 in finite time. Sorry, in asymptotically, in an asymptotic way. So this h is unknown to us. So now what we have to do is we have to select the desired poles, desired pole locations, which is called as the observer pole location. That observer poles need, the number of desired observer poles equal to the number of plant poles. If it is a second order plant, then you have to take the second order observer poles as well. If it is a full order observer, so then what I will be doing, I'll be going to do is I will ensure that in the left hand side I will create the desired poles. I will create an equations with respect to the desired force. And here also, I will, if it is a second order, H1 and H2 will two gains will be there. And I will equate the left half side and right half side. So n number of equations and n number of variables will be there. So unique solutions you can obtain. So if that is the way to obtain this observer gain. Once this H is obtained, then we can always play around uh, with the simulations to see what is happening with the response. So it is quite straightforward when it comes to the simulations and so on. So we will consider this a simple example. So consider the pendulum plant given by phi double dot equal to minus g by L into sine of phi t. For the simplicity, so this, if I represent in terms of state space, yesterday we have seen how to represent this for the double integrator plant. So it is almost similar, phi double dot, but here it was 0 plus something. So here also what we assume that this is my x dot. As far as this observer design is concerned, we don't much have to worry about how the control law is looking like, because as I discussed, for the linear systems, control and observer can be designed separately. So we assume here, by assuming that the control is 0, u is 0. So what is happening here is x dot equal to 0 1 0 0. If I convert the system to the state space, you can follow some standard. If you don't know how to do this one, I can explain, but it is better if you can follow some standard basic control textbooks, fundamental control textbooks. So 0 and 1 and zeta. So here you can see that what is happening is 0 1 0 0. This is a matrix, which is a constant matrix. If I theoretically, if I say that my u is 0, but this is affected with this zeta, and this zeta you can see that minus g by L into sine phi. So this L is the length of the pendulum. So the length of the pendulum we can consider it as a uncertain and so on. So this uncertainty. So in a very naive case, or in a very simple case, if I assume, and I am assuming that my output is equal to 1 and 1, the linear combination of the states. So what is happening here is, if in the very nominal case, we'll see my Leuenberger observer, I need A, B, C, D matrices, because since this is unknown input, or we don't know about this zeta, so B cannot, in general, for the observer design also, B is not required. However, we assume that this particular, in the design, we assume that this particular, for the Leuenberger observer, in the design, we are not going to consider this one, and we will see how the performance will look like. So x1 equal to 5, x2 equal to 5. So x2 is nothing but phi double dot. So phi double dot is coming from here. So since x1 dot equal to x2, so that will give us the first state x1 dot equal to 0 into x1 plus 1 into x2. So that's why if I select x1 as phi and x2 as phi dot, and from these equations and from these equations, I can construct this very easily. So this is the output what I'm going to consider is equal to 1 and 1. So now the task is to design the Leuenberger observer for the state estimation and output estimation with and without disturbance. So with and without disturbance means, so what I will assume that in first case, I will design the Leuenberger case, and I will assume that this zeta is 0, and I will see what is going to happen. And the next case, I will inject this disturbance in the system, and I will see the performance. So I will show you, this is the block diagram. So this is the Simulink diagram. So you can see that this is the plant, and the plant has two states, phi and phi dot, and these are the derivatives of phi dot and phi double dot. If I integrate them, I'll be getting the phi, which is the x1, and if I integrating this x2 dot, I'll be getting x2. This has gone to inside to the plant, and there is this tiny switch here. And as we have seen, if I double click this switch, either 0 will be activated, or this disturbance will get activated, or the unknown uncertainty in we can say about this one. So here I am going to see my output, what is going to, how all the states, both the states, and here the y, which is c into x, is going to the observer, and you can see here that not all states are going into the observer. In this very particular case, we have assumed that my output is a combination of the states. Just for artificially, I assume that it is a combination of states. However, one can always assume that only the one of the states like x1 or x2 is only available. So my C matrix either will become 1 0 or 0 and 1. If both the states, if it is not the linear combination of the states, if both the states are, if my outputs and the states are the same, then my C matrix will be identity matrix 2 by 2 identity matrix. Okay, so now what is going to happen here is so x dot, the equations what we have seen, the x dot. If I integrating that, I will be getting, sorry, x hat dot, I will be getting x hat, which is going here. Along with this Leuenberger observer gain, I can see this, I can see what is happening to the outputs, and similarly I can see, what is happening with the estimated states and so on. So this is the basic simulating diagram, which I will give you the skeleton, and you have to do it. So before, the first thing here is you have to run the parameter file, so which you can see here. So this is the parameter file. A equal to 0 1 0 0, so and C equal to 1 1. And this particular example I have taken from the reference book by Schitzel, Edwards, Friedman, and actually this is the 3.3 section. Though they have not given in a very detailed way of the Leuenberger observer, they have dealt with the sliding mode observer itself, but I have taken some information from there as well. And I assume that the desired poles is -1 and -1, the same they have also considered. And this tiny piece of code will give us the observer gain, Leuenberger observer gain. As I told, place or occur. Generally, the difference between the place and occur is you cannot place, if you cannot select the multiple desired poles at the same locations if you use the place command. That means desired poles are -1 and -1. If you use the place command, it is not going to work, because that is the algorithm in that one. So the occur also do the same thing, but it has the added advantage that it can able to deal with uh, multi poles at a particular at the same location. So what I'm going to do, as I told, this is the dual of A and this is the dual of B and the desired poles. So desired poles, I just assume that -1 and -1. So this is the this is the first thing what you have to run. If you run this, all these variables will be in the scope, sorry, in the workspace. And this k underscore Luen, whatever you are seeing, this k underscore Luen, so will be called from the workspace. And this is my plant. You can see that plant as x1 and x2. So the same thing, x1 dot equal to x2 and x2 dot equal to this minus into sine term. What is this f of x? F of x which is coming from here is the sine term. So it is something relevant to this one. So the same thing what I'm going to do. X1 dot equal to x2 and x2 dot equal to the second state x2 dot equal to 1 into zeta. This 1 into zeta is minus g by l into sine phi. I assume that g equal to l in this particular, so that's why I'm getting the unity. So c is this one, and y equal to c into x1 into x2. So the outputs, so the output arguments here is x1 dot and x2 dot. Since I'm getting x1 dot and x2 dot, if you integrate this x1 dot and x2 dot, you will be getting, and the output as well is one of the output arguments. So the inputs are x1, x2, and fx1. If you see this one, you can see that inputs are x1, x2, and fx1, whereas the output of this particular block are x1 dot, x2 dot, and the actual output of the plant y. So this is the Leuenberger observer structure. So this is the Leuenberger observer code. For the Leuenberger observer, if you see this is one x hat dot equal to a into x plus b into u plus h into y minus y hat, y equal to cx. So this is A matrix and C matrix are required. Since this u is 0, so we are not considering this term. So this will become 0 because we are not considering the combined state estimation and control problem. Y hat equal to cx, this we have seen, so this I have written like this, and y hat I have selected c hat into x luen. So this then what I'm doing here is x hat luen dot, so this is x hat luen dot equal to a into x luen. You can see that it depends how you are selecting this. In this particular case, instead of y minus y hat, what I selected is y hat minus y, so that's why the negative of this terms, the negative sign is coming into the picture here, because here I have changed both the terms. Why I have changed here is why I have not kept the standard one, because while comparing with the Leuenberger structure, I want to retain the similar structure of the observer. So that is the reason why I kept here minus here. So this is nothing but, so this is more or less, yeah, this is the same, this and this are the same. Only thing is this y and y hat I replaced y hat minus y. So since y hat minus y is coming, so this plus has become the minus here. So that is Leuenberger observer. And without disturbance, so this is not a control problem. So you shouldn't worry what is happening to your states. Without without any disturbance, you can see that this is the plant state, and the initial condition is 0 and 1.5 and so on. However, if I select the different initial condition points, you can see that the initial points are something like that 0. So what is happening here is after some time, the state is going, the state and the estimated values are almost the same. You can see that means the error has gone to 0 after approximately 5 seconds. This is the case without the disturbance. And as soon as the disturbance comes into the picture, we have considered the sinusoid disturbance. You can see that these are the two states, this blue one and this orange one. So what I want my estimates also to follow this one, but it is not following. You can see that if it is following, then exactly these should be overlapped. So you can see that you can see only one state you can able to the estimation is happening properly, but the other states is not good. So what is the lesson from this particular thing is, if you go for the Leuenberger observer, then it works very well for the nominal case. However, when the disturbance comes into the picture, then it is not possible to it cannot able to eliminate the disturbance. So to run the skeleton code, what you have to do is you have to run the parameter file first, and then develop the skeleton code, and you have to run the file. In the skeleton code, there will be two things. One is the plant, and another one is the observer, and then you have to run that one. I will quickly show. I will quickly show you, the simulations how it will look like and what need to be done. So as I told, the first thing, this I am Leuenberger parameters I am going to give you. I'll be giving you this one. So Leuenberger parameter, you don't have to work anything on this one. Just if you run, then you will be getting this A value, C value desired. Let me clear all. I have not cleared all. So A, C matrix, desired poles, and this is the Leuenberger observer. The first step is you have to run this one. And the second step is I have given you this file. So this is the file which will look like. But inside this plant and Leuenberger, so it will be the same thing what we have seen. You have to copy and paste it. If I run this one, so here you can see that the switch is there. The first case you run with 0 disturbance, and if I'm running this, hopefully it will run. Yeah, it is running fine. If you write the code inside this particular two blocks correctly, then that should be fine. And once if you run this one, then this plot file also I have given. If you run this plot file, you could able to get the two results. You can see the two graphs. So this is only the states, and this is the states versus observed states. And as the same thing we have seen that it is perfectly fine. So in the second case, what you have to do here is you want to see the performance of the Leuenberger observer in presence of the uncertain terms of the faults. So this is the disturbance. So what I'm going to do here is I'm going to activate by double clicking this one. Again, I will run this one, and then I will go to here the plots. And again, if I run this one, then you can see. Since my graphics card is not good in this particular personal computer, so that's why it is taking much time to see this one. But yeah, so the left one, you can see that the left one is only the plant states. And when I overlap the plant states and the Leuenberger observer states in presence of disturbances, you can see that it couldn't able to do the performance very well. And I don't know if I have plotted the outputs as well. No output I have removed. The output you can see from here. This is the output Leuenberger output comparison, the plant output and the observer output. You can see that the plant output and the observer output are not the same. Just to inform you that this there is only one output, y equal to c into x, where c is the linear combination of the states. So x1 plus x2. You can see that one is the plant and then another one is the estimator, and they are not at all, matching. This I want it to match even in the presence of the uncertainty. So this aspect we will see. So this is the limitation why one has to go for the sliding mode observer, because it in the naive form, this Leuenberger observer cannot be able to handle the external disturbance terms. So we will be going to discuss the sliding mode observer in the next. I will be sending you the PDF file, the simulation file, the skeleton of this file, and plot file and the parameter file. So you have to follow this particular. So you have to run the parameter file which is given to you. The only thing is in the skeleton code you have to change the plant as well as the controller, and then run it. Two cases: one without uh, disturbance. The second one is with disturbance. I'll be sending you in another 5 minutes. So please take your time. So by 8 o'clock we will meet. And if you have completed this, if you think that if you have already completed this one, please put it in the chat box or WhatsApp group so that others will also get benefited with this one. Thank you. So I'll be sending you my uh, these files in a couple of minutes in the WhatsApp. All of you, please be on mute unless if you want to talk with me. Otherwise, please be on mute. Yeah, already I sent. Just to save your time, already I copied in my mobile these files. Yeah, so you can use these things. We'll meet at 8 o'clock. So by then, uh, please do the simulation.
Tirupati Rao, please mute yourself. Babu Tirupati Rao,
సార్
mute లో ఉండండి.
Hello. 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 Hello.
Hello. Yeah. Hello.
Professor Barani.
Yeah. Yeah. Please tell.
This is Dr. Sharath.
Yeah.
Hello. So I'm
Yeah. Yeah.
having a
Please.
small query.
Yes.
So this Leuenberger observer can be applicable for nonlinear systems?
No. For the
No.
non-linear
Okay.
linearized system only it can be applicable. You cannot directly apply with to the non-linear systems.
No. So can I convert the nonlinear system to a linear system? Then I can apply this Leuenberger
Yeah.
observer?
Yes. To the linearized system you can apply, and then the linearized
Okay.
observer you
Thank
can
you, sir.
implement on the non-linear system. Yeah.
Okay. Thank you, sir. Thank you.
Okay. Okay.
Sir, sir,
Yeah.
hello. So please, can you send the older version model files?
I
It is
sent the
not compatible.
2011. Which
Sir?
version you have? I sent the 2011 version.
But it is saying that 9.1 model. Please load the older
So,
version. It is saying
so what is the version you have?
2016, sir.
Okay. I will do one more time. Something might have happened. I will send you in a couple of minutes.
Okay, sir. Thank you.
Sir, for your information, even Simulink Online is also working perfectly fine, sir. So I don't think it will be
This
any.
embedded function is working in that online.
Yes, sir.
But
Yes, sir. Yes, sir.
they should have some access of license, right? License. They will be asking some license.
Account, yeah, maybe I'm using from college account. Maybe that. Okay.
Yeah.
Okay, sir.
Hello. Hello.
Yeah, hello.
Sir. This is
Yeah.
Shastri.
Yeah, please tell, sir.
Generally, while designing a controller or observer, first
Yeah.
of all, we have to check for a controllability and observability for
Yes.
the system, whatever may be the
Yes.
physical system. Is it
Yeah.
necessary
Yeah.
to check?
It is necessary to check if your plant is unobservable. Still, you can observe. You can still design the observer, provided your plant is detectable. And the vice versa, if your plant is uncontrollable, still you can design the controller, provided the plant is stabilizable. Stabilizable means if unstable modes are stable, then we call it as a stabilizable, and so on.
Without any singular points, phase
No,
trajectory, without any singular points?
see, suppose for example, if you have some 10 states, 10 state modes, and assume that 3 are uncontrollable modes. And if those uncontrollable modes, the corresponding eigenvalues for the corresponding uncontrollable modes are stable, then you can design the
controller for 10 states.
Yeah, you can design.
Overall
you can design.
system
Only no, 7 will ensure the remaining 3 are, since they are already stable, then the whole closed loop system will be the stable thing.
Okay.
You cannot control the 3 states directly.
Yes, sir.
Because their impact on the closed loop performance will be low. You can play around with the other states.
Is there any control technique to control those 3 states also? Uncontrollable states. May plant
Which is very difficult. Which is very difficult. So we are going against the mother's theory. So it is very difficult.
Okay, sir.
I mean, we are asking a person without the hands and legs to climb the Himalayas. Though it is possible, but it is almost impossible. Yeah.
Okay.
I'll be sending you 2011 version. So guys, you just in a minute it will be there in the WhatsApp. Please check if it is good. So people are getting the results. So getting the results is a tiny part of the complete exercise, but one has to understand the philosophy behind the results. Hussein Sheikh, you just search in the Simulink library switch, manual switch. You'll get that dipole thing what you are asking. Someone is error in embedded hardware setting. I don't know what is this unless I see. Good to see that people could able to replicate the one. I shared the previous version, Pandyaraj, so please check it. Can all of you please be on mute? In fact, I will also go on mute. If someone has, you can just. We'll start our lecture in another couple of minutes.
Hello, sir.
Yeah, hello.
Hello, sir. Sir,
Yeah, please.
while plotting, I'm getting error, sir. The error is
Maybe. Yeah. Please tell.
enough
Please tell, sir.
enough input arguments it is showing, sir. In the
Maybe
line number
as
10,
as
sir.
yesterday we discussed. Please, you can use what I can say that different options in the scope. Whatever workspace we are saving, you can choose the array option, and you can, because in the newer version, so it was there could be some problem if you're using the earlier version. Double click and change it to array, the workspace block in the Simulink.
Which one I have to change, array, sir?
Go to array, use it as an array.
Which one, sir?
Array. Array.
Value, sir. In workspace,
No.
which where?
No, if you double
Sir?
click, there will be some options there.
Workspace.
Maybe you can see whether if you're getting the same thing in the what I can say that in the scope. What you are getting in the scope? Are you getting in the scope right thing?
Scope, empty scope I'm getting, sir. 1 minute, sir. After running the last file, I'm not empty plot I'm getting, sir.
Then some problem is there, sir, which need to be rectified. You please send your file. I will check in the night and I will get back to you.
Okay, sir.
I hope most of you are getting this one. So now we will go to the next part. So which
Hello.
is yeah, hello. Yeah, Venkatesh.
Yes, I have found out, sir.
Yeah.
Hello. Sir, under
Yeah, Venkatesh,
disturbance,
please
it is
tell.
not
Yeah.
Sir, under disturbance, it is mismatching, na?
Yeah,
Sir,
of
but if
course
you
it will.
change the K value, it is match.
Which one?
Then what is the problem? If you
No, what
change the K value, what
no.
100, 1 and 100, it is
You
matching,
change
sir.
you change the disturbance as well to 100 and see what is happening.
Okay. Which means every
So it
disturbance
is
you need to change the K value. That is the main problem.
no. Leuenberger will not work. It is only for the sinusoidal. It might work for some up to certain extent, but not for all.
Okay.
It is very
Okay, sir.
so you K value will give up to certain control only. It will not ensure that it will go to
Okay,
zero.
sir.
The error will go to zero.
Okay, sir.
Yeah.
Okay, sir.
Okay, so I think we are ready for the presentation. So what I will do is I just give me a couple of minutes. I'll be back in a couple of minutes. Okay, so now we will discuss the sliding mode control, sliding mode observer, and then we'll see the performance wise what is happening and other things. Okay, so let me go to the sliding mode things. We are already to the time. Let me share my screen. Venkatesh, somebody has Bhanu has kept the thing. If you change the KLUN, only the outputs are the matching is happening. Maybe in some cases states can also happen, but the provided you cannot always guarantee that the performance.
Okay,
And
sir.
I have shown you only the simple sinusoid waves.
Okay, sir.
But if you use a similar kind of thing, we will see what is going to happen. Okay, so now we will discuss a class of sliding mode observer. So consider a nominal plant x dot equal to x plus bu and y equal to cx, and assumption is that C has full rank matrix, and the objective is to estimate the complete state vector based upon the output and the input only. So this is the fundamental fundamental design of a sliding mode observer. The first thing is what we had to do here is we had to do the coordinate transformation to bring the particular system into a regular form. What we mean here is regular form is, if you see, there should be some how to find this TC. I will give you a small piece of code which you can use. So what the X has been transformed in this by using this transformation matrix. See, TC where TC is invertible, that means determinant of TC is not equal to 0 into X. Why we are doing, you don't have to do the transformation if your C matrix is in this particular format. So in most of the cases, the C, if it is in this particular format or the regular form, you don't have to do this transformation. Otherwise, just for the ease and the presentation, you have to do this coordinate transformation. So the coordinate transformation, so this is a linear transformation. So what I'm going to do here is this TC, once the TC is there, TCA into TC inverse. If I, again, the transformed A matrix I can represent like this, and the TC into B, then B1 and B2, and this C into TC inverse 0 into IP. So it is very important to see that what we are doing here is only the few, what we are ensuring that the first few elements of the C, the first few elements of the C are 0, and the remaining based upon the output, this IP is coming here. So if in this structure, if we could able to bring the system, so that is called as regular form, then that is good. If your system itself is in this particular form, then if your output C matrix is in this particular form, you don't have to do the any transformation. So that's why, so what we have considered here in the, what we have considered categorically the C matrix, intentionally we have assumed it as the combination of uh, the linear combination of the state. So it is not in that form. So you need the transfer function to transform that particular system. So now this is the structure of the, this is the typical structure of the sliding mode observer. So here you can see that A into X hat minus GL into EY plus B into U of T plus GN into V. So the important thing which makes it different from the traditional sliding mode observer is this particular term GN into V. So if you see the sliding mode observer can be expressed as a combination of linear as well as the non-linear gains. So if this particular element, if you make it 0, then the sliding mode observer boils down to the Leuenberger observer. Whereas this Leuenberger observer doesn't have the capability to deal with uncertain uncertain systems, or the faulty system, or the system which is excited by certain disturbance. So inherently it cannot able to do this one. So what, again, for the sliding mode observer, we should know the bonds of, though in this, if you can see that this is a very standard structure, we have not used any that we have not represented any fault or any such things, but what we can see from the earlier thing is there is yeah, if this one, there is some you can see, you can consider this as a disturbance factor, and the bonds of this disturbance should also known to us, like what in the earlier cases. So the bonds we have seen in the sliding mode control, we have seen in the sliding mode control that the bonds plays a crucial role. So bond should be the maximum, the bonded value should be known ahead a priori. So again, I'm coming back. So this is the structure of sliding mode control, a sliding mode observer which has been taken, and we have to take the array dynamics. Array dynamics again we have seen x minus x hat is the error, or in this particular case it is x hat minus x. So the array dynamics is x hat dot minus x dot. So x hat dot you can get it from here. You can see that, whereas the x dot you can get it from the equation what we discussed earlier. And if I substitute and if I rearrange, then it will look like this: a minus gl into c, where this e is x hat minus x. So it is obvious. So the first time I will explain what is happening. In the first time, if you see, this is x hat and the x is coming from there. If I subtracting this here, so x hat minus x, so this a is, if you take the a common, then you can represent it in this particular form. So this is quite straightforward, and this EY is I have written somewhere EY. Okay, I will show you later what is this EY. EY is the output error, so which is nothing but C into x hat minus y. So that is the output error. So that is the error between your observer output and the plant output. And there is this another term, this bu will get because error, because we assume that the control is not the problem, not our main concern. However, in this particular case, this bu, because we are considering the error, so x hat minus x, so this bu whatever you are getting, then this will be subtracted from minus bu from the plant and it will get cancelled out here. So this is the error dynamics. So we have to ensure that how this error will go to zero. If it is a linear case, Leuenberger observer case, what we have seen that we ensure that the eigenvalues of this closed loop plant, if it is negative, you select, then the plant will be stable. That is fine, but due to, if there is some external factors or external disturbances, you cannot able to ensure that the though you may ensure the stability, but you cannot with the bonded stability, but you cannot always ensure that the state error convergence will happen. So in the presence of disturbance, so what we will doing is this another term, non-linear term, what you are going to see here is this non-linear part, gn and v is coming to the picture. If we assume that the positive definite function, Lyapunov function, we are going to see how to ensure the stability of this one. We have to consider the positive Lyapunov function v equal to E transpose PE, where P is positive definite. If you select this P is positive positive definite function, then obviously your V will also be positive definite, because this E transpose E in the scalar case, it will go to square, or if it is the matrix, then the square terms, error square terms will come as a diagonal elements. And if you take the first derivative and if I substitute it the error expression from the earlier thing, so you can see that it is in this particular form we are getting. So now to ensure that the first derivative is negative definite and so on, so what we have to ensure that we have to select this P, the missing terms is P, GL and GN in a suitable way, so that this above expression should be negative. Then the error, we can say that the error in the error system is stable. So the error dynamics is stable. Question mark is what kind of stability? Is it asymptotical stable, or it is quadratic stable, or it is finite time stable, or so on? That need to be, you have to think of it one. Okay, so for a very naive case, we will assume that if this v dot is negative, that means the error dynamics of my system is stable. So the idea, the key thing is, how do I select this one? So this A minus GLC, you can select it if you, this is from the standard pole placement, the thing what we have seen earlier. However, the selection of GN and V is the critical one, which we will, which need to be thought of. So now we will design the sliding mode controller, sliding mode observer for our plant. So you can see that this is the structure, the same structure. What we have seen, this error, you can see that this is C into x hat minus y. So that's what we have seen. The linear part is GL. It can be selected from pole placement, and we'll keep it the same. So the same pole placement design what we have selected, where the sorry, here the desired poles are -1, -1. It is not the +1. Sorry, there is a typo here. So again, we will select the same desired poles -1 and -1, and we will see that whether it will have it can able to deal with the plant or not. And this is the Leuenberger gains, the same. We will be selecting 1, 1. And the non-linear part, we have selected something like this. How they have selected, this is the problem of our interest. This we will discuss maybe tomorrow. I just give you a brief introduction about the selection of this one. So if you see overall this one, so this sliding mode observer is kind of a retrofitted model. Retrofit. One can retrofit in the Leonberger observer model. You can always design. You can always assume that in the absence of disturbance, you just activate the linear part, so which will do the task very well. As soon as if you see the disturbance or there is a mismatch from the nominal plant in the actual plant, then you should activate the non-linear term to handle with that one. So that is the basic philosophy of the sliding mode observer. In the nominal case, if you make this gn as 0 or the nonlinear term as 0, so this particular sliding mode observer will boils down to the Leuenberger observer, and it will work. It will be the same in the absence of disturbance. Both will be the same. So we will see that one as well. And if there is a disturbance, this need to be activated. So what is
Hello,
Krishna
sir.
Jyoti? Could you please be on mute?
Sir,
Unless if
actually, I
there's
have
some
one.
serious. Please let me complete my talk and then we can have the discussion. So this sliding mode, so this nonlinear part can be activated for the real systems. It is something like that only. So because this nonlinear, always you don't want this nonlinear or chattering for your system to see. So as soon as your system sees this kind of non-linearity, sorry, some mismatch between the nominal and the actual plant, then you should activate this nonlinear term for the error convergence. Otherwise, if it is if you assume that if you think that your nominal plant and the actual plant is not that much different, then you can only go with the linear gain GL part. GN part you can assume it is 0. So that is called as a retrofitted model. So you can retrofit any kind of linear model along with this sliding mode observer. So here we have considered the same pole placement or the Leuenberger observer as the linear part, and the non-linear part it is coming from the sliding mode things. So this is the Simulink diagram which you can see here. The plant is the same what you have seen here. The only the difference here is if you see the input, the first few inputs are the very much similar, like Leuenberger, X Leuenberger, Y and K Leuen. But the new terms are, as far as this particular sliding mode observer is concerned, GL is the linear term which is coming. In fact, this GL and K Leuen is the same, which I will show you. Just I kept it in case if you want to use a different linear observer here. And this gn is the non-linear term in this row. Actually it is 2, so which I have hard coded here inside the code. But if you want to see the response of the system for various row, you can see from here. And the output, you can see here that x hat Leuenberger output, if you do after the integration, the Leuenberger observer states will get similarly for the state sliding mode observer. So this is the output, what we are seeing for the Leuenberger output and the sliding mode output as well. And this is the same plant code. So the parameter code here, you can, as you can see that I have used the same, the Leuenberger, where is this Leuenberger gain and the sliding mode linear gain as the same, just to ensure that I'm not doing something drastically change in the sliding mode observer. And the another thing is gn I have selected as 0 1 and p2 which is not much required in this particular case, and the row as 2. So that the 2 value what you are seeing, though I have hard coded, but just I have written for the generic file. So only the things which are of much interest is GL, which is the same as the Leuenberger observer, whereas this GN is the nonlinear term 0 and 1. It is coming something like this. And this is this whatever you are seeing here is the complete function for the Leuenberger observer in the sliding mode. Leuenberger observer is the same. I will not go into that one. So this sliding mode observers are this new thing. X hat SMO dot is the new thing which is coming to the picture, and Y hat SMO. So the output also I want to see, at the same time the state derivatives of the sliding mode observer also I want to see. So this Leuen underscore SMO control I left it okay. So you can change it to observer. So there is not a big problem. So the output, so the input arguments. So these are the output arguments. The input arguments which I need for this particular block are after the integrator, you will be getting this x hat Leuenberger, x hat SMO, K Leuenberger, which is coming from the parameter file. GL and GN are also which is coming from the parameter. This Leuenberger is the same what we have seen, and this is the implementation of cannot able to minimize this GoToMeeting app here. Okay, fine. So this Leuenberger observer, what I'm saying is, first I'm saying that okay, sorry, this sliding mode observer, what I'm saying that C into Y error. So Y error is C x hat minus Y. So this is what we have seen, the EY. So again, you can see that just a minute, I will just move this app. I cannot able to see my desktop. Okay, so the x hat sliding mode. So this is what you can see here, x hat dot. So x hat SMO dot is A into x hat minus GL into EY minus GN into rho. So this U part is 0. And this nonlinear part, what we discussed there, it is the same. And Y hat SMO equal to C into x hat SMO. This is, I think, repeated. No, it is not repeated. So Y hat is, which is going out of the block, which is nothing but C multiplied by x hat SMO. X hat SMO is nothing but the integral of this particular thing. And interestingly, these are the results. What you can see, that one, as far as the Leuenberger observer is concerned, this what you have already seen. But the sliding mode observer will ensure, the sliding mode observer will ensure that all the states will go to 0. At the same time, the output will also go to 0. So this is what we will see in the simulation. And this is mainly happening due to the selection of GN. And how to select this GN is a big question, and that I will tell you how to select maybe tomorrow also. So I will be showing you my simulations. Yeah. So this is the plant, which is the same thing what we have seen. And this is the observer, what you have seen there, what we have just discussed. And now what I'm going to do here is I will activate this one. And I will, if I run this one, and then I will run this code, parameter code as well. Sorry, the plots of this one. So this will give us, you can see that, you know, the property what was missing in the Leuenberger observer, you can see that it is perfect tracking. Initially, it is taking some time, and then the perfect tracking is happening. So both the states of the plants as well as the SMO states, you can see that the tracking is perfect. And if I zoom here, so you can see that there is a slight chattering happening. And this is the issue with the sliding mode observer, like the sliding mode controller as well. However, this chattering can always be, you know, reduced by using various mechanisms. Tomorrow I will tell you one small, if you do small change in the sigmoid function, then this chattering will go off with a little bit sacrifice in this thing. And if I zoom this one, I think one of the states is getting converged here. It is fine, so it is happening fine. But the problem here is you cannot able to see this convergence is not happening. So in the sliding mode, the convergence, you can see the convergence very beautifully how it is doing, even in the presence of the disturbance. So the only thing is you should have the you should know the maximum value of the disturbance, so the bound of the disturbance. So that's what I can say from this particular lecture. So I will give you this skeleton, not now. I will give it to you after my talk, and because I have another 15 minutes to discuss the paper. And after the, you know, after today's session, you can do it at your home, or tomorrow the whole day you can do, and you can reproduce the results in this one. So now what? My voice is not audible. Is it audible or not? Can anyone can respond? Sudhakar is saying that my voice is not.
Yes, yes, audible,
Okay.
audible.
It is
Audible,
Okay.
it is good, sir.
audible, audible, sir.
Sir, thank you. Yeah. So this is what I can tell you about the sliding mode observer. Now I will show you a small recent paper, 2020 paper, and I will tell you how to reciprocate the results from the paper as well by using the sliding mode observer concept. What I mean to say that the sliding mode observer, what you have listened for an hour, this is not the complete sliding mode observer description. This is just, I have gave you just some flavor of sliding mode observer. If you want single input multi output, somebody has written side. So if you want more details on the sliding mode observer, you can refer a textbook. So that is what actually I want. So quickly you can design any sliding mode observer for any of the system by the concept what we had discussed. If you want to dig in much into various property, invariant property, and what is manifolds, and how to select the sliding surfaces, and what is how to reduce the shattering, these are all beyond the scope of this particular FTP, because in a couple of hours I cannot cover the complete things. Now what I'm going to do here is I will just take a couple of minutes of break, and then I will explain you the paper, and then quiz, as I promised, at 8:45 I will start the quiz, and I will send you the skeleton code of this one after after this session is over. So just give me a couple of minutes of break, and then I will start the next session. Thank you.
Excuse me, sir. Can we ask questions?
Yes, please. Yes. Maybe
Sir,
let me complete the 15 minutes paper presentation, and then while doing the quiz we can have the discussion. So in that way, it will not be, others will also not get disturbed. But you can tell
okay,
you
sir.
can tell the question, because couple of minutes time is there. So please let me know your question.
Sir, that nonlinear part of SMO, GN is the
Yes.
nonlinear part of SMO, right, sir? That is different for
Yeah,
every
mu.
system, or
Actually, this mu is the nonlinear part, whereas Gn is again is the constant. Mu, the new whatever the value you have seen, that is that thing. Yeah.
that signum function. Uh, is that different, sir, to every system? We have to choose it
Yes.
differently.
Mostly you can use the signum function, but it will that depends upon if you are closed loop. If you are selecting how you are selecting the e dot, if it is ensuring that if you can ensure that e dot is negative, then the same thing you can see. You have to do the Lyapunov analysis to see the same, if the same structure will ensure your partial derivative of Lyapunov as stable. Otherwise, you cannot able to always do that one. Yeah.
Yes. Are you can prefer any book or any material of this
Yeah,
SMOs? Anything?
that reference book what I kept, the second and third
Oh,
reference, if you see in my slides,
okay, sir.
the third one is more recent one.
Okay, sir. I'll go through it. Thank you, sir.
Yeah. Okay. Okay, so I'll just share my screen. So now we will discuss a recent paper which was published in 2020 January February, and what they have done is they have designed the sliding mode controller for WES system, sliding mode observer, and the same simulations whatever you are seeing there. I don't think it will take much time after after this lecture for you to replicate the similar results. But the new thing what they have done here is that they have real-time implementation. Though you can see that the whatever the problem they have selected is quite standard, wind energy speed I mean WCS system, wind energy conversion system. But two different things they have combined. One, the sliding mode observer, and they have used this for the wind speed computation. So that's what they claim in this paper. So we'll see what they have done in this paper, and how we can replicate that results also. We will see how you can replicate that result. You can see that in a couple of minutes. So how they have published this paper is, initially they have submitted only the simulation paper to IEEE PDS conference with simulation only. And if you submit any nowadays something related to the power systems which can be implemented on the physically, if it is possible, the the scaled version in the lab prototype, then only getting the publications based upon the simulation results is very, very tough as far as the current scenario is concerned. So you have to do some kind of prototype or some kind of what I mean to say, that some kind of hardware results to hardware experiments to validate the results. So this is the paper. I think you can see my screen. Yeah, you can see the screen. So this is the small tiny paper what what you can see here. It is not the tiny paper, it is very big. They have published in IEEE Transactions on Industrial Applications. This is a very standard journal, and it is a recent one. Maybe in February 2020, means it is quite recent, though they might have submitted a year before, but it is quite uh, recent one. I will show you how the things, the concepts what we learned today, and how it can be applicable to this particular system. I will not go into much detail of this system point of view. Just I will tell you what is happening here. You can see that the system is a fourth order system in alpha beta reference frame. I alpha, I beta, omega E, and theta E are the states. First, what they have done is they have designed the control observer for this particular two systems. If you carefully see the first two terms here, the first term here and the first term here are quite linear in a way, because minus rs into is, so r is a constant and this I alpha s is a state. Similarly here I beta is a state, so you can simply write as x dot equal to a into x in this. And these v terms, you can see that what are these v terms are nothing but the inputs, v alpha and v betas. V alpha and betas are the voltages, basically they are the voltages. And these terms, what they have done here is, I will show you, so keep in mind only these two equations. I'll show you what they have done. So they have represented in this particular format. It is equation number 11, so it is not yet, yeah, yes, equation 11. You can see that they have tried to represent this in the linear form, x dot equal to ax plus bu, but there is some other other terms which are not directly dependent on the state, or which is unknown, and other things. They have kept it as a disturbance. So that nonlinear system or the uncertain system what you have seen there, we can represent something like this. So I alpha and I beta are the two states, and V alpha and V beta are the control input. So x dot equal to x plus b, you can write it. But the remaining term, E alpha s and E beta s, they assumed it as an uncertain input, bounded uncertainty. So like what we have learned in yesterday's and today's class, that uncertain terms. So you should be know these bonds of this uncertain term should be known to us. Okay. So again, I'm going back here. So these two equations now, it can be written as x dot equal to ax plus bu in a very standard form, where these v's terms are the inputs, and A matrix is, it will look like minus rs0, 0 minus rs, and these two terms, they consider it as an uncertainty or the disturbance rather, they consider it as disturbance. So now their aim is to estimate the states based upon now current observer. They have to estimate the states, assuming that this at the same time they have to reject this disturbance as well. So they have, so this is the, you know, the observer what they have selected. Again, you can see that the structure looks a little bit similar to the one what we have seen. So ax hat plus, if you want to see what is the structure, you can go to this reference. This is the standard one, and this is you know, their structure, their sliding mode structure. So this L gain I is the constant feedback gain. So feedback gain is very much similar to the one what we have seen, and x hat is I alpha and I beta. So these are the two estimated one, and you can see that x minus x hat and where ex, what is happening, and all other things you can find out. So this is the control of what you should be interested. So this will give you, you know, the complete the LGAN and LS, how to find that one you can see in this paper for more details. So this tells about the sliding mode observer, and further analysis why if you selected this particular thing, whether it is stable or unstable, how you have selected this one is the proof they have given here. They have taken the estimated error, and they have, you know, the derivative they have taken, and they have the similar approach, Lyapunov function they have taken in the first derivative, and they ensured that they have come up with this value L gain I. So L gain I should be the max, since we know the bounds of this uncertain values. So the maximum, it should be the maximum values of this thing. It should be greater than the maximum value to ensure the good stable thing. So this is one thing, and the next thing is what they have done here is estimation of induced speed EMFs. So they have done the speed EMFs estimation as well here. You can see from this thing, and the next thing is what they have done is turbine torque calculation using sliding mode speed observer. So the another speed observer they have used here, you can see that d by dt of omega e hat. So omega e as well as tg also they have estimated here. Omega e also they have estimated here. So how they have estimated, this is the equation. So now you can, if you see broadly, if you see our system, you can see we have estimated by using this I alpha and I beta using the current estimators, and this omega e, you can see that you can estimate, we have estimated this omega e by using this particular equation, and the other equation is the derivative of this one, so obviously you can do it very easily. So, and there are standard so wind velocity, they have used this formula to do the particular, you know, to calculate the steam turbine and other things. In the simulation, what they have done here is they have compared this with EKF based estimation. They have compared with the EKF based estimation or the extended Kalman filter, and these are the different various results. So now what you can do here is, and they have done the prototype as well. Here you can see all the parameters, most of the parameters, this L gain W, what you want, the linear one for the, you know, for the controller design that is given here. So you can easily, now you can easily reproduce the results. So you should focus on this particular plant. As a first step, you assume that this V alpha and V beta is a constant. So this assuming that this is not the control problem. If you can take some reasonably well value open loop control, you assume that V alpha and V beta is some kind of sinusoid or some kind of, you know, a good open loop voltages, and use these particular current observers. So 5 states. So total, if you say that complete X hat dot, it is a combination of the current, two currents. You can see the two current observers, one speed and one theta observer. So the same thing, the two currents observed by using these equations. You have to find out the first two states estimation, and they had done the torque estimation as well. You can use the torque estimation for that one. The estimated torque can be used for the control purpose, and omega estimation by using this particular omega e speed by using this thing. So this completes my today's session. So now I am activating the quiz for you. So let the people write the quiz. Meanwhile, we can have the discussion. So just I have activated the quiz. Now it is active. So okay, so still I'm sharing my response. I will stop my response. So that completes the today's session. So you're free to leave now, those who have some works, and those who have some queries. I'm here for another 10 to 15 minutes. As I promised, I completed my session in 8:45. What I will do is I will send you the skeleton code for the sliding mode observer, not for this WCS. WCS you have to develop on your own, because I think now you have enough sufficient inputs to design the sliding mode observer for any of the plants. Thank you. Yeah, it is the somebody has asked whether it is a similarity transformation. Yes, it is a kind of linear transformation, but you should ensure that that similarity transformation, the main purpose is to keep the C in a particular structure what you have seen 0 and IP in the regular form. For a given set of pole location, the K values are fixed. Yes, K values are fixed, but in that case, the desired pole locations can be placed far away from the origin. Somebody has shown Chevala Venkatramana some error, it is coming. So this function does not fully set the output dimension. So maybe you have to do something there in that one output dimension. I cannot, from this error, I cannot exactly tell what is happening. To get the outputs, what I have to do now? Somebody has asked, I don't know. Invalid use of operator plant.
Hello, sir.
Yeah, Manu.
Sir, it's like a place and a current MATLAB command. Is there any command here in sliding mode observer, like to find GL, GS, GC, GN?
It is actually in MATLAB inbuilt. It is not. GL is the same whatever occur. Or you can use occur or class for the linear pole for the linear. But for the non-linear, just I am worried because I have the codes. I have to take the permission Christopher Edwards has given to me for my personal use. So I am a bit hesitant to share that GN code with the. I will ask him, and if he say yes, then I will be giving you that code tomorrow. So I sent an email to him a couple of days before, but he's traveling. That's what I got an auto response from him. So if he permits, then I
Sir,
can give you
sharing
that
the
GN
code
code.
is not. Sir, is there any reference relevant to that? His
Yeah, in
paper
the
is there,
textbook.
sir.
Yeah, the textbook, in the textbook, everything is in the textbook.
Okay,
But
to find
code
those
he has developed,
values.
so that is his property. So how you have got this GN value is the one some theoretical explanation is given in that book. If you want to develop on your own, you are welcome. How to get the GN is given in that textbook. The reference number 3 and reference number 2, more or less the same thing.
Okay, sir. Thank you.
I hope the things are going well. So I know that it is a bit tough to to grasp whatever we have discussed here. Uh, it is maybe difficult for some of you. Maybe it is okay for the others. But that is how, because in a couple of hours we cannot solve the whole world problems. Just I'm trying level my best to give you the simplest way to at least look into a particular journals aspect, the research aspects, and from here you can continue further. The purpose is not to make you the complete expert, but since it is 2.0, so you may be having a little bit experience in the controllers or the observers what we discussed. Tomorrow I'll be discussing about the fault detection and the reconstruction thing, and then backstepping also I'll give you the theoretical aspect, and then extended Kalman filter. So which I think we could able to justify the complete the schedule whatever has been shared with you. I will try my level best to cover all the topics. Sir, have you shared the cues? Yes, I already shared it a long time back in the morning itself, but however for I'll be sharing it again. Oh my god, 60. Yeah, again I shared the cues link.
Then increase the time by 10 minutes at least.
Sorry.
Increase the time for the quiz at least by 10 minutes. So we're actually eating.
Definitely, I kept it open for 10 hours yesterday. you know. Yeah, I will keep it open. Don't worry. So I will just keep it open for 9:15 or so. Actually, I thought to keep it in the morning, but since you people are in flow, so it is better to have it now itself. Because tomorrow I'll be discussing the fault reconstruction and the fault detection using observers. Somebody has written that waiting for the hint regarding sigmoid function modification to make chat into minimum. Tomorrow I will discuss this aspect. Tomorrow I will tell you a small trick which the people in the sliding mode community they use to it is an heuristic method to how to approximate this sigmoid function. Tomorrow I will discuss that. It is nothing but filtering out the sharp edges of the sigmoid function. I give at most importance to the feedback. If some feedbacks have, if some participants have some concern, then I just personally calls them and I try to correct that one. And otherwise, if majority has some concern, then in the upcoming lectures I try to correct myself. Like people have some issues with the timing yesterday, so I promised that 8:45. So there is again a trade-off. The less time means I had to rush it off. So I cannot do much thing, but that's what Sorry. Skeleton model, I will send it to you another 5 to 10 minutes. And if the system matrix are functional matrix instead of numerical matrix, yes, that means your system is a kind of either linear parameter varying or it could be the nonlinear systems. Yes, the nonlinear state sliding mode observers are also available in the research market. But however, we have only discussed the linear systems which is affected by the nonlinear term. We assumed it as uncertainty or unknown thing, and then accordingly we design. Yes, if the ABCD matrices in general, if they are state dependent or something, yes, there are nonlinear sliding mode observers are also available.
Excuse me, sir.
Yes.
Hello, sir.
Yeah.
Sir, can you please explain any paper on higher order sliding mode control, sir? Because the basics of SM
Yesterday I sent one
getting to
document,
the
right? Sliding mode controller. Yesterday I sent one document.
yes, sir.
You can, yeah, you can just go through that one. Yesterday already I sent one.
In WhatsApp group.
Yeah, of course. Yeah.
Okay, sir.
Yeah,
Thank you,
yesterday I
sir.
sent some interesting paper. Yeah.
Hello, hello, sir.
Yeah, hello.
Sir, good evening, sir. I have a
Good
doubt,
evening.
sir.
Yes, please.
Yeah, regarding the chartering concept in the sliding mode.
Yeah, yeah.
Yeah, yeah. The occurrence of chartering, is it due to the raw data or bad data available in the plant?
No. It is not raw data. It is completely due to the sliding mode, the signum function what you are using. That is due to the
Okay,
signum function. So
okay,
if you smooth sigmoid function, if you use, then chattering problem can be handled up to certain level, but with an what I can say that trade-off that I will tell you what is the small tiny piece of change if you
okay,
do,
sir.
then
Yeah, yeah,
that can be
yeah.
rectified.
Earlier
Yeah,
you have mentioned, sir. Yeah, yeah.
yeah. Tomorrow I will show you that
Okay,
one.
sir.
Yeah,
Okay, thank you.
yeah. Okay.
Net गया क्या? Hello, sir.
Yeah, hello.
Sir, yeah. Same myself. I have asked no one doubt, no, sir. So this is my last question for today.
Yes, yeah.
Yeah, sir. The thing is, whenever we consider, I mean, in a power system aspect point of view, whenever we consider some three bus system, five bus like that. So
Okay.
whenever we are with the fault analysis, so short circuit
Uh,
faults. So yeah, here we are discussing the plant is one aspect and this, I mean, observer, I mean, sliding mode or Luenberg or whatever it may be, the controller. So,
okay.
so the entire power system has to be considered in a single plant, sir. The outputs which you are obtaining.
Okay, there are two particular aspect. One is called as a lumped system, and the another one is a distributed system. So the complete power
Yes, sir.
system, yes. As far as for complete power systems is concerned, in the literature, people have considered it as a one single system. But suppose for various, if it is an area system, the system structure will look the same, but the parameter of that, if you see the two area system as well, so more or less it is the same system. However, if you see for each of the systems, like area 1 and area 2, the parameters could be the different. So what generally represent is, instead of the A matrix, B matrix, C matrix, D matrix, they represent sometimes it's summation of AI. So
Okay,
several systems can be they can be combined together based upon the system at your hand. Otherwise, it
okay,
can be considered as the
But
the
whatever may be the number of whatever may be the system. I mean 5 bus, 9 bus, 14 bus. So but the
yeah
system is complex, no sir. But the system is
yeah
complex, no.
yeah
Then how do we
yeah.
analyze with respect to these observers or controllers?
No, first of all, you have to see the system could be the complex, but what states or what the
Okay.
outputs are playing a crucial role. If it is, let us say, 500 states are there in general in the industry, not all the 500 states one need to control. They have to see what are the
Yes.
critical states based upon the plant at hand. So then you have to,
Okay.
what
Okay.
are the systems? Just now we have seen WCS, it has only five or six states, but they are not the
Yes.
only states. There may be some hundreds of other states which are not playing a significant role in the overall system's
Yes.
response.
Okay. Okay. So we need to find out what are the critical states, and for that critical states, we will be applying these
Yes,
controllers or observers. Yeah.
yes,
Okay.
yeah. That is the
Okay, sir.
standard thing.
Yeah.
Hello.
Okay. Okay, sir. Okay. Thank you, sir. Thank you.
Hello.
Yeah. Hello.
Sir, good evening, sir. So, sorry,
Good
the
evening. Good evening.
13 buses in a power
Sorry.
system, 13 buses are there.
Yeah.
Hello.
Yeah. 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 Please tell, sir.
So, circuit breakers are there. Suppose LG fault is there. So, how the
Uh-huh.
observability is working on this condition? Relay, how it will sense the relay in this
Sir.
condition? Suppose LG fault is there.
Yeah. Sir, actually, I'm not from that. My research area is not in that particular area. So sorry, I'm cannot able to. I'm not the right person to answer your query. Because I don't know the much insights of that one. If you ask me some control and their application, straightforward application, I can tell you, but not
Sir, I belong to
I
power
don't have.
system.
Yeah, but I don't have that expertise, sir, and that actually the scope of this particular FDP is also beyond that one. That is not my expertise, and I cannot give you the suggestion in that aspect because
Okay. Thank you.
yeah.
Okay, thank you.
Yeah.
Sir, this is Ravi Kiran.
Yeah, Ravi.
Sir, are there any cases where we cannot apply sliding mode observer, or like
Yes, you cannot apply some
are there any
cases like
cases
yeah. If
non-linear
you cannot
systems,
bring
like
your
class of
if you
non-linear
cannot
systems?
if you cannot bring your if you cannot bring your system to the regular form, it will be very difficult and complex. Otherwise, you can apply to any systems. And the non-linear systems also you can apply. There is non-linear sliding mode control is very matured one. You can apply. There is uh, practically where you cannot able if you cannot able to reduce your chattering beyond certain level, then it is not suggestible to use that one.
So for this such type of controllers, like systems, which one may be applicable?
That depends upon because if the chattering if you think that really it is a very much concern, and if you want to go with the robustness, you can go for the H infinity controller, which has or the mu synthesis and mu controller and so on.
Okay, everything depends on the system only, right?
Yes,
So
yes.
how do we
So that's why
identify such like? Do we need to go for literature, or will there be like just by looking at the problem itself, we can see
no the
which type of
problem
controller we can apply?
by looking at the problem at your hand, the requirement, because the state system can be the same, but requirement might changes from time to time. So that also need to be looked into it.
Okay, okay, sir.
So please do share this sliding mode observers PDF.
Yeah. In another 10 minutes it will be there.
Thank you.
Just I'm creating the skeleton. Somewhere I missed the skeleton. I don't want to send you the actual files because I want it to work. So just I'm creating the skeleton and I'm ensuring that it is working fine.
Sure, sir. Thank you.
Sir, can you explain how to find capital T, sir? Transfer from
Sorry, sir.
transformation matrix. Sir, I have given in the box. Message.
I will explain you tomorrow with a suitable example, sir, because the transformation matrix need to be selected. There are various theories are available. So one I can select by using the controllability and observability analysis. From that controllability Gramian and observability Gramian, you can select it. That aspect tomorrow I will discuss, sir. I don't have the slides now with that one because it is mathematically intense. I'll explain tomorrow, sir. That.
Okay, sir. Okay. Thank you.
Kasim Shakiru Olaji, sir, where does the error falls if the system is saying that their model error in a design? Kasim, it is a bit difficult to tell you what is the problem. Error falls if the system is saying that their model error in design. Model error can be due to the hundreds of reasons. Until I see your the file, I cannot able to tell you. Okay, I'm signing off. Thank you. Thank you all. We'll meet you tomorrow at 6:30. Bye.